In this video, we want to make sense of the average value of a function. So let's say I have some function f of x. So here's my graph of y equals f of x. And I want to think about it on some, let's say, some range from a to b, some interval a to b. And so here's my function from over here at a to over here at b. And the function goes up, it goes down, all kinds of different values it takes. What is the average value of the function? Well, maybe it's not obvious what the average value of the function is, right? Like you might say it's the lowest point it ever reaches. The lowest value is, I don't know, maybe here, like the lowest value is some, I'll call it m for minimum, right? And so this is like my minimum value. This is my minimum value. And then there's some highest value up here. Maybe I'll call that like big M for maximum. Okay, so maybe that's kind of silly using M twice, but little m for minimum value, big M for maximum value, right? So the average value of the function is probably somewhere in between. But where in between is it? We're going to use the definite integral. We're going to use the definite integral to help us make sense of this. So recall the definite integral, the integral from a to b of fx dx represents the area under this function. It represents the area between this graph and the x-axis. Now, how does that relate to my minimum and my maximum value? Well, if I think about this minimum, and I imagine there just being a line across at y equals this minimum. So I just create a line here. Y equals this minimum. Then right here, I get a rectangle whose area is the height of your minimum times the width b minus a. And since this is the minimum, I know that every point on this function is at or above this line, which means this area must be greater than or equal to the area of this minimum, the rectangle of minimum height. Similarly, if I come up here to my maximum value, big M, and I draw a line across there, I can also think there's a rectangle here now whose height is now big M. So here's a big rectangle. So its area is big M for the maximum times the width, b minus a. But since every height of my function is at or below, this should be at, right, on the line, or below the line, this area under the graph will be less than or equal to the area of that big rectangle. Will be less than or equal to the area of the big rectangle. So the area of this guy is somewhere between the minimum height times b minus a and the maximum height times b minus a. Somewhere between those. But that means, by the intermediate value theorem, there's some special value, there's some special height, somewhere between the minimum and the maximum, so that if I drew a line at that height, and I drew a rectangle, I could pick the height so that I get height times b minus a comes out to be exactly equal to the area under the graph, the definite integral. So the minimum is too small, everything is less than or equal to the area, the maximum is greater than or equal to, but there's some height between the minimum and maximum that when I do that height times my width, the area of this rectangle comes out to be exactly the same as the area under the graph. And so I'm going to define that height h, I'm going to think of that height h as being the average value. So I can move this to the other side by just dividing by b minus a. And so I have that this h is my average value. It's the average value, h, this was an h. Ooh. This is an h. H is the average value of my function. Okay, so there's my formula for average value. Let's do an example to see if we make sense of this. So let's think about a nice concrete function. Let's just draw part of a circle. You know, we just draw here a quarter of a circle. Let's say we want to go out to, I don't know, 2. So it's a circle of radius 2 centered at the origin. So what is the equation of this? That's going to be y equals x squared plus y squared is 2 squared is 4. So y is the square root of 4 minus x squared. That's the equation here to get this quarter of a circle. And I want to know, what is the average height? So this circle, it goes from, this piece of the circle, it goes from height 0 all the way up to height 2. Where's the average? You know, is the average at 1? Is it above 1? Is it below 1? What is the average? Well, we're going to calculate it using our formula. We're going to say the average height should come out, the average value of this function between 0 and 2, from x equals 0 to 2. It would be a different answer if you're going all the way from like negative 0, or all the way from negative 2 to 2. But just from 0 to 2, it should be the guy who is 1 over 2 minus 0, 1 over 2 minus 0, times the area from 0 to 2, this area under here, times this whole area, so the definite integral from 0 to 2 of 4 minus x squared dx. And what does that come out to be? This is just 1 over 2. This is just 1/4. So let's think about what this represents. This piece here is just 1/4 of the area of the circle. And area is pi r squared. So pi times 2 squared. But that's just 4 divided by 4, so it comes out to be just 1/2 pi. These guys cancel, giving you just 1/2 of pi, or pi over 2. So pi is 3.14, so pi over 2 is something around 1.57. So right around here, you know, that's actually pretty high up. So right around here is pi over 2. So maybe that's kind of surprising. That's saying your average height is actually this height right here. This is your h. So in order to get an area that's the same as the area under the circle, you need a pretty tall rectangle. Not one. It's not halfway up. It's higher than halfway up. And the reason you should think of that is because there's more area on the bottom half of this graph than on the top half. And so you need to go more than halfway up to make sure the area of your rectangle is the same as the area of the circle. Okay, so I was able to find the average height. I was able to find the average value of this function between 0 and 2. What you might recognize then is there's actually a point on this graph. There's a point, there's some x value here. There's some value between 0 and 2. There's some x value. So the height of the function actually has your average height. That is, instead of thinking of this as just being some h, what I'm saying is there's some value c, so that f at that c actually comes out to have your average value, 1 over b minus a times the integral of a to b of f of x dx. So this is for some c between a and b. So like in this example, we can solve it out explicitly. We can say, when does 4 minus x squared square rooted, when does this guy have height pi over 2? Pi over 2. And we can find the x value. So that would actually give you your value of c. So maybe I should call this c. I'm trying to solve what is the particular x value c that gives this to me. And you can solve this out. You know, you square both sides. 4 minus c squared is pi squared over 4, and then you solve for the c squared, so these can switch, giving you c squared is 4 minus pi squared over 4, which if you want to simplify that a little bit, that's 16 minus pi squared over 4 is c squared, because 4 is 16 over 4, and then you just solve it out, and you get your c is equal to the square root of this. It's the square root of 16 minus pi squared all over 4. Or if you prefer, you can think of that as 1/2 the square root of 16 minus c squared, because the square root of 4 is just 2. So the square root of the bottom becomes just 2. Well, there's your c. You know, however you write it, your c here has an exact form of 1/2 times the square root of, that shouldn't be a c, that should be a pi. This is pi squared of 16 minus pi squared. So there it is. There's the x value. And yeah, this is some number between 0 and 2. Pi squared is a little bit more than 9. So 16 minus pi squared is a little bit less than 7. It's 6 point something. The square root of that is 2 point something. 1 over that's 1 point something. So there's some value here, 1 point whatever it is, that has as its x value your average height. Okay, so this is saying there's some x value so that f at that x value comes out to give you your average value of the function. Now, this guy is called the mean value theorem. But this should set off alarm bells in your head because you already know a mean value theorem, right? If you think back, we already had a video about the mean value theorem. Before, if you think back, that what the mean value theorem had told us previously is if I had some function, I could find the average rate of change. That would be given by some f of, if it's going from a to b, my average rate of change is f of b minus f of a all over b minus a. And then the mean value theorem said there's some special point c. So there's some special point c between a and b, so that the tangent line here is the same slope as that average. So f prime of c. So this was the mean value theorem we saw before. This is the mean value theorem for derivatives. Instantaneous rate of change is equal to average rate of change. And you know, if you squint your eyes a little bit, it kind of has some of the same features as this one. In a couple of videos from now, you'll actually see that these have a lot more in common than it seems like now. But you just see now both are dividing by b minus a. Here it's f of c, it's f prime of c. So it's not quite the same, but there's a good reason they have the same name. And we'll come back and have to talk about that more in a few videos after we talk about the fundamental theorem of calculus. But just keep in mind, there's a mean value theorem you've had before, which was for derivatives. Now you have a mean value theorem for definite integrals, okay? And it's just saying that there's some point between your a and your b where the height of your function at that point is equal to the average height of your function. So if you draw a rectangle at that height, it'll have the same area as the total area under the graph. Of course, all of this discussion is only true when f is continuous. If f isn't continuous, then you're not guaranteed any of this. Your function could have breaks and jumps, and maybe you can't find such a point c. But if your function f is continuous, if this is a continuous function, then you can always find the average height, and after you find the average height, you can find the point where your function achieves that average height.